Hello and welcome to the Chapter 4 podcast on Section 4.4. Today we're going to be talking about oxidation reduction reactions. Oxidation reduction reactions, which are also sometimes referred to as a redox reaction, is basically a chemical reaction where electrons are transferred between reactants. Okay, the substance that loses electrons gets oxidized, the substance that gains electrons gets reduced. Okay, so this is kind of shown in these figures on the right and also on the bottom. Here we have calcium and oxygen. So oxygen is doing the oxidizing, taking the electrons away from the calcium element, producing an ionic situation where you have calcium, the ion, the +2 ion, and now you don't have oxygen anymore, you have oxide. Okay. The easiest way to identify what was oxidized and what was reduced is to apply oxidation numbers to things. Oxidation numbers usually correspond with charges, but not always. For atoms and their element, and these are what I have here listed are rules for assigning oxidation numbers. For elements, the oxidation number is 0. For monatomic ions, the charge is the oxidation number. Non-metal ions. Nonmetals usually have negative oxidation numbers, although they can sometimes be positive. Oxygen is almost always -2. Hydrogen is almost always +1. And it can be -1 when it's a hydride or bonded to metals. Fluorine is -1 in all compounds. All halogens are -1. The sum of oxidation numbers for all atoms in a neutral compound is always 0. And for polyatomic ion, the sum of the oxidation numbers adds up to the charge. So these are the oxidation numbers kind of in short, and there's more detailed lists as well, but in general these are what we're going to apply. Metals can be oxidized by acids and by other kinds of compounds as well. This is known as a displacement reaction. If you had honors chemistry last year, you probably remember this as single replacement reaction. We never really described it as a redox reaction, but it actually is. A plus Bx becomes Ax plus B. So what ends up happening is the metal replaces the hydrogen ion in the acid, if it's an acid, and for a salt, the metal replaces the cation in the salt. So here are two examples of this. So zinc plus hydrobromic acid gives us zinc bromide and hydrogen gas. If we look at oxidation numbers, zinc is 0 here, hydrogen is +1, Br is -1, zinc goes to +2. Notice how bromine's oxidation number is still -1, so it doesn't change, but hydrogen goes from +1 to 0. So we can look at oxidation number changes to identify what was oxidized and what was reduced. Whenever the oxidation number increases going from left to right, that's an oxidation. Whenever it decreases, that's a reduction. And if you think about it mathematically, that adds up, right? We can also have metals and salts. So in this case, manganese will replace lead, and so in this case, the lead takes electrons away from manganese, resulting in manganese nitrate and lead. Manganese goes from 0 to +2. Lead is +2 because the nitrate is -1 as a total in terms of its charge. Individually, oxygen would be -2, and the nitrogen would be +5, but it doesn't change as you go from left to right. So manganese, notice how it increases, so it's oxidized, and the lead is reduced. Here's an example of a redox reaction. So let's say we had magnesium and cobalt 2 sulfate. Magnesium, when it ionizes, will become Mg2+. Cobalt sulfate is the result of cobalt ions and sulfate ions combining to form COSO4. The molecular equation is listed here. And then I showed the complete ionic equation. So remember, as before, anything that is aqueous here gets dissociated into their ions. And then we have the net ionic reaction as well. And again, notice how sulfate is the sole spectator ion in this case. In terms of oxidation numbers, magnesium starts out as 0 and becomes +2. The cobalt starts at +2 and goes to 0, so oxidized and reduced again. Not every displacement reaction necessarily goes Some metals cannot be oxidized by others, and this is something known as an activity series. Basically, any active metal, any metal that's more active than the one it's trying to replace can actually replace. But if it's a less active metal, then it cannot replace the ion. So, for instance, here's the net ionic equation where copper can replace silver, but silver is not as active as copper, so it cannot go in the reverse direction. To know whether or not a metal can go, this is our activity series. So basically, for instance, lithium is the most active metal. It can replace anything below it, but since it's above everything, nothing on this list can replace lithium. Similarly, gold can be replaced by anything, but it can't replace anything itself. And then things like, for instance, aluminum. Aluminum can replace anything below it, but nothing above it. And we'll work with this in class so you kind of get a better idea of what this is. There is an exception to this. Nitric acid and copper is a special exception. And I bring this up because, again, you're going to have to know reactions for the AP Chemistry exam, so I thought I would bring this up. In this case, hydrogen is below copper on the activity series, so this reaction shouldn't be able to go from the perspective of the cation and the atom, but because of the nitrate and the oxygens on it and the activity of nitric acid, it is what oxidizes the copper. So notice how you get some copper nitrate, but notice how some of the oxygens become other things, and this is because of donation, because of the stripping of electrons away from the copper. And this is not a simple oxidation. It's much more complex, and it kind of goes a little beyond the scope of the course, so I'm not going to get into too much detail. But suffice it to say, the metal's oxidized by the nitrate ion as opposed to the hydrogen, and that is it.